Hello, everyone, and welcome to the MMID Coding Workshop series. Our instructor for today is Molly Pratt. She is a graduate student in the Department of Medical Microbiology and Infectious Diseases at the University of Manitoba under Dr. Gary van Domselaar. Today's workshop is going to provide basic set of instruction to the tidyverse package in R for reshaping and combining metadata associated with biological research. All right, Molly, the floor is yours.
Thank you, Grace. So welcome back, everyone, to the coding workshop. Today, we're going to be talking about, as Grace mentioned, tidy data and combining and transforming data using R. So just some information for participants and some housekeeping. All of the workshops in this series are being recorded and they're going to be posted to the MMID Coding Workshop YouTube page. Please mute yourselves and keep your questions to the end of this workshop. There will be time for question and answer at the end, and that portion will not be recorded. So last week, Grace gave us a wonderful introduction to R and RStudio. So if you haven't already, I would suggest watching that video for the workshop at the link here before jumping into today's R code. And some things that Grace went over last week that are going to be important for this week's workshop as well include RStudio navigation, installing and loading basic R packages and libraries, how to use base R functions and operators. And she also gave us a nice introduction to R scripts and R Markdown. For today, we're going to use some example data in order to become familiar with tidy data structure. We're also going to discover some R packages for data science, and these are called the tidyverse. We're going to use functions from the tidyverse packages to reshape some example data and to combine more than one data set. And we're also going to get a little bit of practice modifying variables and making some new variables within our data. So what is tidy data and what is the tidyverse? I'd like to start by mentioning that most of the material from my introduction today is adapted from the book R for Data Science, and specifically chapter 12 on tidy data. So I really encourage everyone to bookmark this free online resource. It's been immensely helpful to me when I was learning R. So there are 3 rules of tidy data. First, each variable must be saved in its own column. So in this example, we have 3 arbitrary variables and they're called F, M, and A. Secondly, each observation is saved in its own row, and this means that the rows are going to be independent of each other, and all the information you need for a particular observation is going to be contained within that row. Finally, each value is contained within its own cell. So if any of this is confusing right now, don't worry. Hopefully it will become a little bit clearer when we look at some example data. Another question you might have is, why do we want data to exist in this type of format? Well, tidy data works best with the vectorized operations in R. So for example, let's say that our M variable contains mass data and our A variable contains acceleration rates. So in R, we can calculate force in a new column simply by multiplying our columns M and A. This is going to preserve all of the observations, no matter how many there are. So imagine you have thousands of observations, and this is a real time saver. Now, sometimes in order to make our data into a tidy format, we need to reshape it into a longer or a wider format to satisfy those 3 rules that we just talked about. And if you're having trouble understanding what makes a data set tidy or not, I have a little test that you can use. So you can pick a column in your data set and just ask yourself, do the cells in this column contain values of the variable? So let's look at an example. So if we look up here at table 4, we can see in the farthest right column that the numbers in this column don't make sense as values of a variable called 2000, right? That doesn't make intuitive sense. So instead, we can look at the tidy version of the data set, which is outlined in green here. And we can see that 2000 instead is a value of a year variable, and that makes sense. And those numbers that we saw before are actually values of a new variable, which is cases. In table 2, over here, we can do the test again. So the first 2 columns are going to hold up to this test. So Afghanistan, Brazil, and China all make sense as values of a country variable, and likewise with the year. However, the last 2 columns are not going to hold up to this test. So I encourage you to compare these example small data sets with the tidy data sets in green, and that these outlined in green data sets should pass this test. You can also try this at home with your own data sets and think of how you could turn them into a tidier format. So the tools that we need to create and work with tidy data are available within the tidyverse. The tidyverse is simply a collection of R packages, some of which are shown here, and they're designed specifically for data science. So the packages share an underlying design philosophy, grammar, and data structures, meaning that they're all designed to work with tidy format data. You can install each package individually or all together by installing the tidyverse. So in the introduction today, I'm going to focus on a few specific packages and functions within the tidyverse. And throughout the workshop, I'll point you to some external resources where you can get more information on other packages. For example, packages and tools related to visualization are going to be covered in later workshops in this series. So remember that you can install and load all of the tidyverse packages and their dependencies with 2 simple commands in your R console. Notice that you need quotation marks in order to install the package, but not when loading the library. So the main packages that we're going to be using today are Reader and ReadXL for reading and writing our data tables into and out of the R environment. We're also going to be using Tidier and dplyr for data manipulation and cleaning, and Stringer for manipulating character strings. And I find this particularly useful when working with healthcare data, such as patient information or other non-numerical data. And just a reminder, cheat sheets for using these packages can be found online in the workshop materials for today's workshop, or through RStudio, as Grace pointed out last week. I highly recommend using these cheat sheets. As you learn, they're extremely helpful. So each of the packages we'll be using today contains functions that allow us to manipulate our data. And I want to give a couple of quick notes about function syntax before we begin. So you can specify the package name in your function call, as all of the examples on the left are done with the package dplyr, or you can simply write the function without the package name. So the former might be easier when you're still learning about different packages, or you might have multiple packages that have a similar function name and you can differentiate them in this way. So when we're in the tidyverse, typically the first argument in your function call is going to be a data frame, which is denoted by an X here. And this is followed by any additional arguments you may need. In the examples on the left, the data frame X is called iris, and I've highlighted that in green. And then the additional arguments are highlighted in orange. And you can see, for example, that the distinct function requires no additional arguments. Another way to write functions in R that's especially useful with tidyverse functions is using pipes. So a pipe is denoted by the %greater than% symbol. And all it does is it takes that first argument X outside of the function. So if we say this out loud, use X to do F with Y is the same as saying do F with X and Y. So it might be a little confusing at first, but piping makes R code much easier to read and organize, and hopefully you'll be convinced of that throughout this workshop. So the functions in the tidyverse allow us to manipulate our data, such as subsetting observations or variables, or making new variables based on existing ones. The tidyverse also contains functions for combining data sets, and there are several different ways to do this. So we're only going to look at one of these today, but I encourage you to reference the data wrangling cheat sheet for more information. Also, if you need more information about any particular function, you can simply type a question mark followed by the function name into your R console, And after hitting enter, a help page will appear for that function. The help page is going to list all required and optional arguments, as well as the default settings for that function. And it's followed by examples of how to use the function at the bottom of the help page. So this is a really great resource that you can use in RStudio as well. One more quick note before we dive into some data transformation. So we saw some examples of this last week already in Grace's workshop, but I just want to give a brief overview today since we're going to be using the syntax regularly as we work with data frames in R. So when working in R, it's often useful to assign the output of a function to a new object in your R environment. This is a great way to save intermediate outputs or steps when you're writing a whole script, for example. So as an example, we can use the base sum function to calculate the sum of 5 numbers like so. So simply typing the function and the arguments into your R console is going to print the result, which we can see is 15. Now, if we use the arrow operator, we can tell R to save this output in a new object, which we're calling B. And you'll notice that when we assign new objects, nothing is printed in the R console. Instead, in order to see the contents of our new object, we just type its name into the prompt and the output is printed just like before. So last week, someone asked a question about saving certain settings within R. So for example, if you ever find yourself typing the same function with the same arguments over and over again, saving your output as an R object is one good way around that. And just note that you can easily overwrite your new object by assigning a new value to it. So here we're overwriting the contents of B with a new value, which is B plus 10. And now when we enter B at the prompt, the new value is printed. In order to preserve your old objects rather than overwriting them, simply just change the name of the R object on the left side of the arrow operator. So if we were instead to call our new value B10, we can preserve the old value of B. So we type B into the prompt and we see the original value, which was 15, and we can type B10 and we can see the new value of 25. When you're working with entire data sets and not just single values, I would definitely try to avoid overwriting your intermediate outputs until you're very familiar and comfortable with the code that you're writing and using. This is because it becomes much more difficult to troubleshoot. If something goes wrong at a certain step, you have to completely start over rather than just referring back to your output for that step. So it's a little bit like version control. If you're worried about memory or space on your computer, you can always remove those intermediate outputs when you're finished and you've achieved your final product. So now let's get into some data transformation, and we're going to use some example data to do this. So the materials for today's workshop were emailed out earlier, and they're also available on the GitHub page for this workshop series. The materials are contained within a couple of subfolders like so, and the files that I've bolded here are those that we're going to use for today's exercise. An example of the final output is also included for you to compare with your own, and there are some extra cheat sheets in there included for your future reference, or if you just need more help with a particular function. I recommend that you download the workshop materials and save them to your working directory. So if you already have an R project started for this workshop series, you can just save this folder in the same place as the R project, or you could create a whole new R project for today's code, or of course you can work without an R project at all. So I encourage you to open the R script in RStudio and work through it on your own time. In this workshop, I'm going to give a basic explanation of each function. However, more detail is included within the R script to help guide you when you're doing it on your own. So first, we're going to take a look at the data that we'll be working with in today's workshop, which is these two data sets here. So let's imagine you're a scientist interested in studying isolates of influenza A virus for an epidemiological study. So you've downloaded a subset of flu isolate sequences from GISED, which is a data sharing platform that focuses on viral sequence and epidemiological data. And in addition to the viral sequences, the EpiFlu database allows you to download a table of metadata associated with each isolate. So metadata is a set of data that describes and gives information about other data. So for example, if your data is a book or an article, the metadata would include descriptions of that book or article, such as the author, publisher, year, keywords, genre, and other information that would help a librarian to either locate the specific book from a bunch of books or to possibly group it with similar books. When we're looking at sequence data, the metadata might include descriptive information such as the taxonomy or subtype, the host that the sequence was isolated from, the location and date of sampling, and any other information that's going to help scientists to give context to the sequence data. So it's this metadata and not the viral sequence data that we're going to be working with today. So for the purposes of this workshop, I've downloaded metadata for a few dozen flu isolates from GISED, and these are in XLS format. There are 63 columns of data in this table describing 41 flu isolates. The columns contain a variety of information from location and date of sampling to host information and even some drug resistance profiles. So let's say that you're interested in a subset of this metadata for your hypothetical study. Now let's say you've also done some kind of preliminary analysis of your flu sequences using some kind of bioinformatics tool. So for this example, I use the influenza classification suite, which is available as a Galaxy workflow. If you have access to Galaxy, you can look for this tool by typing flu suite into the search box. So this workflow takes as input one or more influenza sequences, and it outputs something called a line list, which is in CSV format. And this line list contains taxonomic clade assignments, as well as information about our sequences as they relate to a reference sequence. So because this newly generated information describes our original sequence data, it can be thought of as additional metadata, and it makes sense to add this information to our existing metadata from GISED. So what we're going to be doing today is combining this line list with our GISED metadata. So we can take a look at the line list output. You'll notice if you open this on your own that there are 137 columns of data in total. So here I'm just going to display the beginning as well as the end of this data set. I'm definitely not expecting you to be familiar with this type of output per se, just giving a quick overview today so that we can understand it as a starting point for our data cleaning steps. So if you were to open the CSV file in Excel or other spreadsheet software and look through it, you would see information about a reference sequence at the top, including the amino acid identity at specific positions. Below these first two rows, we can see information regarding our flu isolates, including the original sequence name and the new clade assignment. Now, the majority of this line list contains amino acid substitution data for particular antigenic positions. And for our purposes today, let's say that we're not interested in this detailed positional information, but we do want to keep the first few columns as well as the last two columns, which tell us the total number of amino acid substitutions, as well as the percent identity with the reference sequence. So now that we have our two files containing data about our 41 flu isolates, we can begin working in R. So first, we're going to load the reader package into our library in order to import our lineless CSV file into R. So please note that you must have already installed reader or the entire tidyverse prior to running this first command. Once we've done that, we can load the CSV file into R using the read CSV function, and we'll assign it to a new object in our environment using the arrow operator here. We'll call the new object line_list_raw so that we can identify this as our original starting point, aka our raw data. And within our call to the read CSV function, we need to first specify the path to the file that we want to read into R. You might need to modify this path slightly if you've downloaded the workshop materials to a different directory. Then we add a comma and a few additional arguments to our function call. So recall that the first two rows of our line list contain reference sequence information only. So we can tell read CSV to skip those first two rows using the skip argument here. This is followed by another comma and then an optional argument I've added, which is show column types, and I've set that equal to false. This is just going to prevent R from printing out all of those 137 column types in the console as the data is being loaded. So next, we're going to use the view function to open our raw line list in RStudio's viewer. The data is going to open in a new tab, and we can see that since some of the columns in our original data did not have names, R has assigned new names for these columns corresponding to the column's position, and this is denoted by 3 dots and a number. You might see a message related to this print out in your console. Now we can load our other data from GSED into R using the readXL package. So first we load the library, and then we point to our metadata Excel file using the readXL function. And we assign it to a new object, which we're calling GSED metadata raw, just like before. There are no additional arguments needed for this function since this file has a very straightforward layout. So using view again, we can open our raw metadata in a new tab. You certainly don't have to use view every time, but if you're a visual learner like me, I find it helpful to understand each change that we're making to the data set. So if both of your data sets have loaded correctly, you should be able to see your new objects in the Environment tab in RStudio. You can see that the names of the new objects are just as we've specified, and the value corresponds to what we were expecting. So next, we're going to remove unwanted columns containing position-specific amino acid data from our line list using dplyr functions. So first, load dplyr into your library, and then we can create a new object to store our data frame in. Again, I strongly advise against overwriting your raw data, so we're going to call this new data frame line list keep, since it's only going to contain the columns we want to keep for subsequent visualization or analysis. Feel free to get creative with your object names in R. So I'm using a pipe here before the function, and this is telling R to do the next operation on our raw line list here. I'm highlighting all of the pipes and functions for this workshop in orange so that you can clearly see each function call. So we're using dplyr's select function here, and all we need to do is provide the names of the columns we want to keep. So we'd like to keep the sequence name column, the clade assignment column, the number of amino acid substitutions in the antigenic sites, and the % identity of antigenic site residues. So while you're typing all of this out or listening to me say it, you'll probably notice that some of these columns have really cumbersome names. So we can change that using another dplyr function called rename. All we have to do is add another pipe at the end of our select function, which is telling R to use the output of this function as the input for the next function, which is rename. So first we're changing sequence name to isolate name, and that's just so that it's consistent with the metadata column containing the same values in the GSED data. And I'm also changing the names of 2 other columns in order to make them shorter and easier to type or read. So notice that I'm avoiding spaces in my column names using either underscores or periods so that we don't need to put our column names in quotation marks anymore. The syntax for renaming columns is always going to be new name =, old name. So now if we view our new data frame, we can see that it contains only 4 columns now with the new names that we specified for 3 of those columns. We can use select on our metadata as well, this time using column position numbers to specify the columns we want to keep so that we don't have to write out the names of all the columns. Note that you can also rearrange columns within this function as well. So I've placed column 12, which is the isolate name, at the beginning of the data frame. We can confirm that this worked by viewing our new data frame. So next, we want to combine our 2 data sets into a single tidy data table. In order to combine them, we're going to need one variable to act as a key that uniquely identifies each observation so that R can match observations or rows from each table. So let's use isolate name as our key variable since it uniquely identifies each observation in both data sets. Remember that both of our tables contain metadata on the same 41 isolates. Before we can go ahead and join our two data sets, it's worthwhile to check whether the values for isolate name are actually the same in both of our tables. So to do this, we can create new objects, A and B, and these consist of an alphabetical list of the isolate name values from each table. So recall from last week, we used the $ to extract a single variable from our data, and then we can pipe these values into the base function sort, which is going to alphabetize the list. Note that these are some of the vectorized operations in R that I mentioned earlier. Once we have our two lists, we can use another base function, summary, to tell us how many values from A have an exact match in B using the double equal sign here. When we type this in, we get a printout in the console, and from that printout, we can see that 7 of our values do not match exactly. So we're going to need to address this before we can join our data tables. There are many ways that you can look at the values in order to determine how they're different. You could manually inspect the data sets in the viewer in RStudio, or you can practice your R coding to print the values into the console. So as an example, I've chosen to just print a single value from each list, and we can see immediately that although the isolate names are similar, one uses a space and the other uses an underscore to separate words. So this is easily fixed using the stringer package. In this next line of code, we assign new values on the right side of the arrow to the existing isolate name variable on the left side, which is this is going to replace those old values. So the str, or string replace all function, is going to look for every space, that's our first argument, in the character strings, and it's going to replace them all with underscores, that's our second argument. So if we run this, and then we rerun the 3 lines of code above, we can now see from the printout in the console that all 41 of our observations have exactly matching values in our two data sets, which means that we're ready to combine them. So all we need to join our data sets is a single line of code using the full join function from dplyr. Notice that I've chosen to omit the pipe in this line somewhat arbitrarily. Since this is only one line of straightforward code, I don't think that piping makes it any easier to read or understand, but you can absolutely try writing it with a pipe for your practice. We input to the function the two data sets that we want to join, and then we use the by argument to specify our key variable, which is isolate name. You can use view to see the join metadata table, and you can also confirm that the join was successful by checking the new object in your R environment tab. So our combined table has 41 observations and 21 variables, which makes sense because we had 21 variables from one table and 4 from another, minus 1 duplicate copy of that isolate name variable, which was present in both of our tables. Now, you may want to clean up some of the variables within the data, even if they're technically already in tidy format following those 3 rules we discussed. So we can do this using functions from the dplyr and the tidyr packages. As you can see on the right side of the slide here, some of our values have been entered inconsistently, and this happens a lot with health data, leading to different possible formats for our variables like date, gender, and age. This can be problematic when you subsequently try to analyze or visualize your data, so we're going to clean them up using some consistent rules. We'll make a new data set called metadata clean for the output of these steps. Again, you could simply overwrite your old data set, but while you're learning, I recommend just creating new objects every time you change something, even if it feels tedious. This is just so that you can troubleshoot more effectively and get back to where you started really easily. So the first function that we're going to use is mutate. And this might look a little bit scary at first, since we've got multiple nested if-else statements going on. But once you become a little bit more familiar with R, I promise this is easy enough. And I wanted to give an example that's a little bit more advanced for you to grow into. So I'm going to go through it one by one. I'm changing 3 variables with this call to mutate. First, we're using the substring function to extract the first 4 characters, starting at 1 and ending at 4, of each value in the collection date column. So if we look at the raw data in the collection date column, we can see that although there's different formats for each of our values, we can see that extracting the first 4 characters of each substring is going to give us the year. So I'm calling the new column collection year. Next, I'm using a couple of nested if-else statements to create 3 defined categories for the gender values. So essentially, if-else statements look at the values of a specific variable, and then they modify those values based on the rules that you give. So here I'm modifying the values in the host gender variable, and the code reads out like this. For all observations, check if the host gender is male or M, and if so, set the value to male. If else, if it's neither of those case values, then check if host gender is one of female or F. If so, set the value to female. If else, if it's neither of those cases above, check if the value is something other than NA. So we're using the isNA function here to see if the host gender is not NA, if it's equal to false. It's a little bit of a double negative. If it's not NA and it's not the cases above, set the value to other. And if it's none of the cases that we set out previously, then you can set the host gender to NA. So finally, we're creating a new variable containing the host age in years. So what this does is it uses another if-else statement to calculate new values if the host age unit was originally given in months. And then it will take that age and divide by 12. If it was not originally given in months, then just keep the host age value. I've added an additional argument as well at the end of our mutate function using the .keep equals unused argument. And this just tells mutate to get rid of the old columns that we use to create our new ones. You can set .keep equal to used if you want to see the variables before and after side by side in the same data table. Then we can clean up one last column, location, which contains different levels of information across observations and will be difficult to visualize or analyze as it is. So we pipe our output from mutate directly into a new function, separate, and we specify that we want to separate the values in the location column into 3 new variables, which we're calling continent, country, and region. And currently, these are all divided or separated by the / character. So R is going to use this information to separate out the values in this column based on that / character. Note that not all of our observations here have region information available. So you might get an R warning message print out in your console telling you that R has replaced these missing values with an NA, and that's just fine. So now it's a good idea to view your clean data set and confirm everything is the way you want it. If you go through the R script on your own time, I've also included a couple of extra steps in there at this point for you to play around with the data a bit more. In order to illustrate how this metadata might be used downstream, let's say we want to annotate a phylogenetic tree of the flu sequences with our metadata. Note that visualization is going to be covered in a later workshop, and this is for example only. So if we were to display the raw collection date and location values next to the tree, you can see that we get a very messy display. It's not easy to visually interpret, even though our data was technically in tidy format at this point. However, after cleaning up our data, you can see that it's now much easier to visualize with those discrete categories. So here we can see our cleaned data set, and it now has 25 columns. So remember, in the previous code, we made 6 new variables and we discarded 5 old variables. And the data is looking pretty good right now, and we probably could save it at this point. However, I would add one last optional step before we save the file. So you may have noticed that several of our variables are related to each other. So for example, some contain host information, while others contain isolate information or related data. So I would add on one final rearrangement before we save our data set. You can rearrange columns by their position using select, as we have done previously. As a note, everything following the pipe here could easily just be added to the end of our data cleanup steps in the last code chunk, and that would eliminate this intermediate metadata clean data set. Then, of course, it's good practice to have a final glance before you save to make sure everything's in order. And finally, we can use the write CSV function to save our metadata final R object as a CSV file that can be opened using Excel or your other software. So in addition to specifying the object that you'd like to save, the write CSV function also takes a location where you'd like to save the file. The location goes in quotation marks, and it consists of an existing file path, or if you don't give it a path, it will be saved in your working directory. And this is followed by the new name that you'd like to save the file as. So if that worked correctly, you should be able to use the graphical user interface, aka the file explorer, to locate your new file. Right-clicking on the file is going to show you options for opening that file. And since this is a CSV file, Excel or whichever spreadsheet software you use should be one of those options. So this has been an introduction to tidy data and the tidyverse. You should now be prepared to go through that R script on your own and practice some cleaning and combining of data. There are many additional resources out there to help you get started in R, and I've included a few of them here for your reference. So in addition to some really great free online books, there are several websites such as datacamp.com that offer free beginner R tutorials with guided practice that will get you more comfortable with hands-on coding in R if all you need is practice. If you'd like to know more about the Galaxy project, which I mentioned earlier, there are many free training resources offered for that platform as well on their website. And finally, don't forget to save the cheat sheets from this week's tutorial or bookmark the web pages. They're really comprehensive, and I basically always have them open when I'm working with the tidyverse. In case anyone wants more information on the data sets that I use today or the tools, I've included some references here for you. And that's everything. Thank you so much for attending. I'm going to stop the recording now and we can begin the Q&A session.